and thank you very much for the invitation. I'm really happy to be here. The talk is mostly about repeated games and how people learn in the specific context of transportation networks. But I thought what I would start to do first is kind of a how did we get there type of recap, because the transportation network evolved radically over the last 10 years. So if you think about the traditional approach to instrumenting the environment, in which the state DOTs would deploy sensors, whether they're static, whether they're hardwired or wireless, in a sense, this is the way public agencies have been thinking about it for the last probably half century. And of course, if you look historically at the rise of the mobile internet, and you might recognize on this chart devices that are pretty much vintage, like the Commodore 64 or other things that you might have used to play video games back in the 80s. The smartphone, the rise of the smartphone has completely radically changed transportation in a quite unexpected way, in the sense that it was not designed for it. So first, I'm going to talk a little bit about Mobile Millennium, which was the project that started all this back in 2008, in the context of how the smartphone evolved in its ecosystem and its capabilities. So you can see this is right around the time when the iPhone was launched. The first iPhone did not have a GPS, and where it led and where we are today. This is the outline of the talk. A little bit about the historical perspective. Then I'm going to go into the core of the new mathematical model that we're trying to put together to model how companies that route people in the transportation network, in a sense, might be modeled, and then talk a little bit about heterogeneous games and what that means for congestion. So Mobile Millennium was the first traffic app ever launched in North America to gather probe information from GPS-enabled smartphones running on Symbian and RIM. This was one of the phones it was running at the time. It looks like a vintage object, good for a museum now. The first launch was actually from the Berkeley campus. We had 5,000 downloads, and very quickly, which was huge at the time, which of course now is ridiculously small, and very quickly was bootstrapped by a lot of other feeds that the company of the time, Nokia, was gathering. Of course, Nokia was the giant cell phone provider at the time, and so that enabled us to transition from this, which unfortunately is still alive, but in this form, but which was a traffic information website back in the 2008, to this, which was probably in California the first ever traffic information system that was powered mostly by mobile data. And of course, now all of you have this on your phone. It's something that is very classic, but we had a lot of fun building the first prototype. And I'll just tell you about this in 3 slides. Working with some of the agencies that are in the field at the time was challenging, in the sense that they wanted proof that probe data could be enough to feed a traffic information system, which now has become a reality. So back in 2008, we rented 100 cars and asked 200 students to participate to a gigantic field experiment where they would be driving back and forth on 10 miles of freeway, in the hope of creating a situation in which the penetration of vehicles equipped with these devices would be around 2%, which was the 18-month forecast of what penetration rate would be at the time. So Nokia wanted to know whether 18 months from that time they would be able to run a system with roughly that penetration of phones. Now the penetration of phones is probably over 100%, because people have multiple devices in their cars, and cars are connected. But then of course it was a different story, and so this is what the experiment looked like back in the days. And in order to corroborate everything we're gathering, we also had dispatched crews of students with video cameras on the bridges to film everything, so we would have access to travel time of all the vehicles on the freeway. This is the depiction of what the 100 vehicles were at the time. Each of the dot was one of the vehicle carrying a phone. We were holding a press conference with a deputy director of Caltrans and the CTO of Nokia back then, and displaying to the press in real time what probably was the first time ever in history that you had a live display 100% fed by mobile data, so there was no static data at the time, that was broadcasting traffic information in real time. And the experiment lasted for 10 hours. There was a major accident in the middle. We ended up catching it right before the police. But that's good, because in a sense, for 10 minutes, people thought the system was going south. Everything was breaking. That person who used to work at traffic.com was calling the traffic.com headquarters to check on the accuracy of our information. People were starting to get nervous, and my blood pressure was going up until we found out that there was an accident, because pagers, which is another defunct devices of all the police that was there, started beeping 10 minutes later. And so at that point, we figured out we had captured an accident faster than the traffic information systems at the time. And the rumor, since Balaji's in the room, is that Berkeley did the accident on purpose to demonstrate the technology. And my response to this is that the rumor, of course, came from Stanford. So we built several generations of that system, which is a fairly common build now. The person who built that is now at Apple Traffic, and there's a lot of similarities we can see in the way we built this and what we see on Apple Maps nowadays. So you have feeds, which of course are heterogeneous, that are put into filters, models. We heard a very nice LWR model that we use a lot in the previous talk, estimation and forecast, and target customers. This is what 0.5% of our data was. That's the percent we could show at the time. This is many years now. So this is about 500 taxi vehicles that were connected using some similar software in San Francisco. Red dot is a vehicle, black dot is a GPS track every couple of seconds. You can imagine, I mean, Uber has thousands of vehicles now in the city, all connected to Waze and many other devices. So you can imagine the amount of data that is available today. At the time, if you had plotted that data over the course of a day, this is the granularity you would have seen. So it was already quite high, not high enough to reconstruct flows, high enough to reconstruct speeds and travel times. Of course, companies like Google nowadays, through their apps running on all platforms and through their own platform, Android, probably have near 100% penetration rate if you accumulate everything they have. So in a sense, the problem has changed from estimation to, or for estimation from very low penetration to very high penetrations. And so where this story fits is really, you know, at 2% penetration rate. So that means if 2% of the vehicles have a device that sends data, that's what you get. So this is a time-space diagram. It's a common tool used by traffic engineers. So you have time, you have post-mile, and a dot represents a GPS track every couple seconds. And then the color indicates the speed. This is for the day of the experiment. You can see the accident in the morning, congestion picking up, not really recuperating throughout the day, and then evening congestion picking up again. And so the type of work that we did in the last decade on this was, well, if you decimate this data, so here it's decimated spatially, could you reconstruct what the traffic was? And again, very important 10 years ago. Nowadays, you could argue with the penetration of GPS, maybe it's not that important anymore. But using models just like the LWR model that was shown by Balaji in the previous talk, this is what we could reconstruct. So if you run extended Kalman filter, or actually in that case, ensemble Kalman filter, because it's nonlinear, non-smooth, on a discretized LWR PDE, so the very hyperbolic system you saw before, you can pretty much reconstruct the entire flow pattern really, really accurately. So we were very excited, and people, you know, started asking us, well, how do you compare to Google? So we used to, for a couple months, be faster than Google. So this is an example of what a Google feed would be every 30 seconds back in 2011. This is what our feed would be, and what you would see with the models is that when an accident happened, you can see the shock wave grow really fast, and it would take another 15 minutes at that point to appear on the Google feed. That's because we had faster data and also much better models with LWRPD. Of course, this was many years ago. There's an army of people at Google who built a really phenomenal engine, and now their engine is quite nice. And so I think it's fair to say that at this point, if you think of the evolution of technology over the years, the years of 2008 and 2009 was really the boom of the action in terms of traffic estimation. Like, how do you take traffic information? How do you make it into a valuable product? And these are the companies that worked with us or hired our student over the years. And in a sense, I think that field is now very mature. And I think the game is about to change again, because there are companies like Google who now have the ability to almost see everybody who is moving on the freeway. So the game of trying to reconstruct traffic from a very specific penetration, which used to be low, to reconstruct flows, maybe is not so much relevant anymore when soon there will be access to every possible vehicle in multiple ways, not just one feed. This is kind of what you see when you see the rise of the number of users of phones in the US. Back in 2010, in Luxembourg, you already had 150% penetration. That means 1.5 phone per person, and this is in 2010. So you can imagine with connected vehicles and the mobile internet nowadays in the US. That work also served the state of California in its procurement, in its very first historical procurement of data. So the type of work we would do for them then is try to help them evaluate, what is good GPS data to buy, what's bad GPS data to buy. For example, that feed that we were evaluating always has a latency of 5 minutes. 5 minutes makes GPS almost obsolete if you want to do real-time traffic management, because you've seen the rapidity at which traffic jams develop. You need to have it instantaneously. Or this other feed, was showing high penetration rates during the evening and the night because it's a trucking company. Again, not very helpful if you're building a live engine to monitor traffic. So these are the type of criteria that we were trying to build. And so over the last decade, a lot of the work went into finding the right mathematical models to integrate that data to provide accurate estimates and finding the penetration rates at which you would be able to achieve a certain accuracy and for specific cost. So that's the estimation problem. How from a data like this, potentially decimated, you build something like this. And then, okay, the question is, could you do it for control? So in a sense, if this is your traffic patterns, could you be able to reduce congestion in some specific places, remove congestion in other places? And again, using the models that we heard from in the previous talk, the LWR models, there was a lot of work over the last decade in terms of creating optimal control algorithm to change these patterns in any pattern you would want. So, of course, being very patriotic, we chose this pattern. So what this is an example of, I would say, congestion on demand, in which, so you have a freeway again. So this is a pretty long freeway with a bunch of on-ramps and off-ramps. This is time. And this is, if you take the LWR equation, like we heard before, you discretize it, and you put adjoint bit optimization on top of it, either MPC style or even offline, you can show that, provided you have the right demand, you can create pretty much any patterns you want. And so there's a lot of work still working in ramp metering right now. This was one of the first time that we were able to show that we could achieve almost any arbitrary pattern, provided you had a good calibrated model of the freeway. That got the reviewers mad, and it took us 3 years, I think, to get that paper published. But at the end, it was published. So one of the work that we've been working on for a while now, together with many other faculty, Praveen, Roberto, and several others, was a project in which now we'd like to use this at a broader scale to manage a corridor. And that means try to find a way to control all the different assets of the corridor, which in the present case are mostly traffic lights and metering lights, in order to make the traffic flow better through the corridor. There are a lot of reasons why you might or might not want to do this. For example, the planning agencies in San Francisco might not want to decrease the congestion level in the city, because if you decrease congestion, in a sense, latent demand will provide more people to come to the freeway. So there's a lot of debates whether reducing congestion should be a goal in itself or whether it should be other metrics. But either way, this is a gigantic optimization program in which you're trying to assemble all the different assets you have, so local lights, potential routing apps, which are becoming, in a sense, the next way to manage traffic, and several other things that you can either instrument or optimally control. And that brings me to the actual core of the talk, which is, it's 2016. For many decades, we believed that with public agencies running infrastructure, you could control mobility. But the reality of things is that who controls mobility today? Whoever provides you the app you have on your phone that tells you how to get there, which basically means that mobility, the control of mobility, is switching from something which is government owned by something which is private sector owned, and which is not collaborative in nature. And that's the motivation for the work we're doing right now. So if you think of the simple problem of routing, what planners do nowadays is they have what they call OD models, origin destination models, and they solve something which they call user equilibrium, which is a dynamic traffic assignment. It's, in a sense, a Nash equilibrium over resources that people are competing for, which means if you live here, if you work here, you're all competing with everybody else in the city for the roads, and in a sense, you're trying to accomplish what's best for you, which is the shortest path to get there. So you can think of this problem as a problem in which you have a distribution of flow, and the flow goes from origins to destinations. It can choose different routes, and at every iteration, say at the end of the day or at the end of your commute, you experience a certain latency. So in the past, you used to get that information from the agencies, but nowadays you're getting that information from your phones. And it's unclear what it does to the system. And so it's an interesting problem to model. Well, from an academic standpoint, it's a repeated decision-making problem, but also it has a lot of practicality. So the way to model it is, there are entities who are controlling the flow. So if X% of you are using Waze, you're going to follow the Waze routing. And if Y% use Apple Maps, you're going to use the Apple Maps routing. So there's entities that, in a sense, control mobility. And these are the entities that allocate these flows. And at the end of the day, whether you did good or bad, you know about it. And so you have your own policy to figure out what you're going to do the next day. And what you're doing the next day, so it's like you're the way you're routing the flow at the next day, depends on how you did, what you did yesterday, and what you experienced yesterday. And so now the question of doing this optimally for society is, in a sense, designing the right feedback that can achieve that optimally, where optimally is defined by you or by whoever wants to do something optimally. So this is a repeat. You could view this as a repeated game, and one of the interesting things is, how could you design these allocation schemes in a way that achieves certain objectives optimally, and people will not be collaborating. There's no reason for company A to share what they're doing with company B if they're competing for that business. So in a sense, you only know what you did, you only know what you experienced, or if your company, you only know what you told your users to do and what they experienced, but you don't know what others did. And so you can see how that can be decentralized, and you can plug different information patterns. So this is a very good metaphor to what happens on your phone. When you type routing requests in Google, it usually gives you the shortest path. That's here to go to Stanford. And it usually gives you near shortest path, like something which is a nearly equivalent ETA. And these are the second or third best choices that Google typically gives you. So what is that? That is usually a shortest path algorithm running on a travel time distribution, which could be either predictive or just static, depending on the company. But it's not something that results from, in general, solving a dynamic user equilibrium, because the data is not available at global scale. So this is practically selfish routing. So this is instantiation of a realized Nash equilibrium in which everybody will choose what is the best for them. So now, there are a lot of companies in that business. These are the typical suspects that you probably are running all on your phones. And each of them have a percentage of the market. Waze is very popular. For example, most of the Uber drivers nowadays use Waze to route themselves. That means there's probably a lot of Waze users in the cities where Uber is very present. Google is global, so in a lot of places in the world where there's no other agencies, then that's what people will use. So each of them has a certain percentage of the market, and then each of them will route their own set of internal users. So say 8 of you are using Waze, you might not all get the same route if you go from the same place to the other same place. So they'll route their flows in a certain ways, which is the way they choose to route people. Now, in an ideal world, in 10 or 15 years, they would probably all of them be solving a dynamic traffic assignment problem, which makes things globally. But nowadays, you're getting your best route, which by definition of what you want is selfish, because you don't want something that is good for society. Well, you want that too, but okay, maybe the first priority is to get to your destination as fast as possible. And so, in a sense, what these are doing is they're all competing for the same resources and all contributing to a Nash equilibrium. So non-cooperative game in which they're all playing against each other. And so the model I'd like to show now is a model of this phenomena, which is what happens in our routing system. And so I'll go back to the process in a minute, but the main issue with this is, first, it's not even clear whether that converges. Because you could see, say on Monday a company routes everybody on 101, then it's really bad, so you learn. So on Tuesday you'll go on 280, but now everybody's going with you on 280, so it's bad. So on Wednesday I'll come back to 101. So that process of iterative learning, which is what's in a sense happening, it's not even clear it converges to anything. So the notion of designing a proper feedback and learning mechanism so that they can learn over time should hopefully lead to at least some notion of convergence where we can say, well, this is converging to something, which hopefully will be a Nash equilibrium. And then you could try to do better. You could try to do something which is optimal. And so that's kind of the core of the work here. So going, yeah.
I think you're right that there was sort of periodic learning going on, but now most of these guys pretty much do real-time updates on their maps for 15-minute levels, or even 5 minutes or
even faster, yeah.
But I think the main point, the other point you're making, I think is really important, which is they don't have the same view. They don't have enough representatives out there giving them the data that they need. So Waze has an understanding of one portion of the network. It's different from Google's understanding.
Well, they're the same now, but because they were acquired by Google. But
they're not linked up.
Yeah, exactly.
They function differently.
Yeah. Yeah.
But nevertheless, I think that's very interesting. Modeling that or
and it also, each company does not know the other company's learning model. I mean, they have different learning rate. Some might be more adaptive than others. So understanding the assumptions that one can make to see where that converges and how that converges is still an open problem, and it's going to be an ongoing problem because each of these companies' strategies are going to be better. Yeah.
Regarding the different learning model again, so you mentioned Waze has a data set which is different from, say, Google's data,
or Apple, or
but on the other hand, like what is a real-time data, for example, Google is getting? Suppose I have an Android phone, and suppose my Google map is not on.
Yeah.
Still, Google is getting the navigation data
Sure.
that I'm using.
Sure. Yeah.
Even if I'm not using Google Maps, I'm providing this data to Google.
Right. So everybody's providing their data to most of the major companies. If you have an iPhone, Apple gets your data. If you're running a Google app on an iPhone, both Google and Apple are getting your data. And if you're running an Android, regardless of the app you're running, Google is getting your data. That data provides, at best, representation of traffic now, and if you have predictive models, for example, time distributions, whatever they are, Markov chains or whatever you use, you could also see this as predictive. Okay, that's different. That's the traffic information layer. Now, when you query Google for a route, it queries their system and their models, whatever their models are, and it provides you the shortest path for you, or the fastest path for you, because that's the main product that everybody's producing. So the work is basically trying to model what happens when everybody is using more or less the same product. So it's like everybody's getting the shortest path or the fastest path from a company, regardless of the models they're using, regardless of the data they're using. Some crappy company might have a really poor model, poor data. Google, phenomenal models, phenomenal data. So some get better than others, but everybody is trying to get the shortest path, and that's what it models. So there's going to be tons of questions because everybody is an expert on traffic and has questions about this. So I'd like to walk through some of the talk, but I promise you'll be the first one. Or go ahead. Okay, one more. Yeah.
It's not even. It's more to back you up. I mean, like, so I was at Berkeley for 4 years. I went to like a talk by one of the execs at TomTom. And essentially, what they do is, they do shortest path based on their data that they have. Their models require 10% penetration.
Okay.
What they do is they just buy off Vodafone.
Exactly.
They buy Vodafone traces.
Exactly. Yeah. Yeah, exactly. So every company has their own little cooking. They buy their ingredients. They have their own ingredients which they collect with their own tools. Yeah, everybody's more or less doing the same. And at the end of the day, what you are all doing is you're all querying their system, which provides you the most selfish thing, which is what's best for you, which is your shortest path. And that's what this models. And so, so the first question is, now that everybody's doing this, what does it lead to in terms of convergence? So can you find a class of feedbacks such that the state of the system, which is the flow allocation, converges to something? So that's the state, that's the flow allocation over all the origins and destinations. And we want this to converge to something. We don't know what that something is. And depending on the assumptions that you make on the feedback, which is the way people learn, you can prove stronger and stronger convergence to what will end up being a Nash equilibrium if you make certain assumptions. And that's the contribution of this work. So first, what is a Nash equilibrium? So lots of you have heard it in the context of routing. It's an equilibrium of traffic in which there is no incentive for you to deviate. So Google gets you a travel time using a path. If you deviate from that, your outcome is worse. So there's no reason for you to deviate. That's one way to look at it, which you can characterize in terms of the reward function and any deviation from the equilibrium leading to a penalty that you don't want to incur. And there are links between the Nash equilibrium and first-order optimality conditions in optimization, which are fairly well known. So first one, so I'm going to go through 3 different classes of feedback, which are ways to model what companies learn over time, and see that the more assumptions and the stronger the assumptions, the better the convergence. So the first one is what's called the no-regret policy, in which all you require is that you don't have any regret, which means over time, if you were playing the best thing but always the same, then you couldn't do better. So that's called a no-regret policy. That's encoded by this here. What you can show is that if you have a no-regret policy, then you can guarantee that the average of the state is converging to a set of Nash equilibria, which, by the way, might not be unique, and in general will not be unique, because obviously it's a very underdetermined problem. Okay, so what does that mean? That means that on average, so if you just make that no regret policy, so you assume that the choices that these companies make every day are no regret, then on average, the system is converging to a Nash equilibrium. So that's very interesting from an optimization perspective, but that's very bad for traffic. So it's a very simple example here, which I'm going to illustrate. So we have one origin, one destination, another origin, another destination. I can go this way and this way for the red. I can go this way, or that way for the blue. And I'll come back to what these weights are later. Convergence on average is actually bad because, in a sense, this is a thing which we can see happening. So in that example, you have proportions of traffic that vary. Let's say, example, I said Monday you do this, Tuesday you do that, Wednesday you do this, Thursday you do that. So on average, it converges on average, but in terms of the traffic, it's terrible because basically you have terrible oscillations of traffic. So this is just a very simple illustration of why, if you make weak assumptions on the process, then you have convergence on average, which is great because, in a sense, from an optimization standpoint, that's a gradient descent problem. So if you're just trying to optimize a function, in that case, that'd be the horizontal potential, you can show that it's a good gradient descent algorithm. You just keep taking the average and you'll get to the result. But from a modeling perspective and as an analysis tool for traffic, it's bad. So it will converge effectively on average, but it will never converge in terms of the state. And so that shows that, you know, if people don't have any rules in the way they or have weak rules in the way they learn, then this could lead to very bad instabilities. So now we make a bit stronger assumption. That's the second part. Now say we assume that the learning phase has a very specific structure. And that structure is called the hedge algorithm. And the hedge algorithm is essentially saying that your decision at the next stage with your flow allocation, if you're a company, is proportional to what it was before, multiplied by an adjustment factor, which is proportional to your reward. So it's saying, okay, well, if you did really bad on this route, you should take it into account, and you should maybe have less flow through this route. But then you adjust it by factor eta t, which comes from what's called the hedge algorithm. And you need to make some assumptions on eta t. So you could view eta t as your learning rate, and you want your learning rate to ultimately go to 0, which means basically at some point you've more or less converged, you're happy with your solution, and that's how you learn over time. So it's a stronger assumption than the previous one because now you have a structure in that learning that is explicit, which actually ends up resulting from what's called the replicator equation. That equation is a discretization of the replicator equation. Just rewriting it in a certain case, you can add some stochastic noise to it to add some convergence features. But you can see that now that learning structure is actually stronger. And then what you can show with this is that now you'll have a stronger convergence to the Nash equilibria. And for that, you need to have some assumptions. So in particular, you need some assumptions that you make on your perturbations. You need some assumptions that you make on your learning. In particular, your learning needs to go to 0, but in some, it needs to diverge. And that's a bit technical, but that's important. And then what you can prove with that is that now you have almost sure convergence to the set of Nash equilibria. It's still not unique. There's tons of Nash equilibria. But you have convergence almost surely, provided that your learning rate goes to 0, but you have to go to 0 not too fast. You still have to be able to diverge. And the way to prove that, which is a much stronger result, is that, so basically the way you do it is you discretize the ODE, the replicator ODE, which I showed before, and then you show at every iteration that your discretization doesn't diverge too fast from the continuous solution, and these are the continuous and the discrete solutions, and that shows you the convergence. So you can prove it. Yeah, 5 minutes?
What do you call convex potential case?
So in the case of routing, there is something called the Rosenthal potential, which is a convex function, which if you optimize, so basically the cost is the integral of the link cost, where link cost is actually the travel time on each of the edges. If you optimize that function, which is convex, then you get the solution to the Nash equilibria. So there's a complete one-on-one mapping between the solution of the Nash equilibria and the solution to that convex potential, which is what that function is here. And I can explain more later, but basically, in that case, it's nice because solving for the Nash equilibria is a convex program, and that's been known since the 60s. So, and that actually is nice because that brings me to the last model, which is, okay, now that we have that equivalence between the Nash equilibria and the solution to the Rosenthal potential, so F is the Rosenthal potential, then you could view this computation of a Nash equilibrium as solving a convex program. So for this, so now the good news about this is that there's tons of algorithms that are very efficient at solving convex programs. One of them is mirror descent, which is yet another way to model the same problem. So you could view this iterative decision process as a step of a mirror descent algorithm, where the mirror descent algorithm is a classical thing that is often used to solve a convex program. So basically, at every step, your iteration now, once you have identified how much cost you incurred in the previous iteration, is minimizing the sum of these two terms, which is basically your loss plus some Bregman divergence, ponderated, weighted by 1 over eta t, where eta t is the same learning rate as in the previous thing. So obviously, now this is even more specific than the previous one, because now you have a very, very specific update rate. And you can view this as a way for your system to learn what happened before. This is the graphical illustration of what mirror descent is. In a sense, you're approximating your convex function by something which is also convex and with a Bregman divergence. And then you can see how, because if you've done any convex optimization, you could decentralize this. So in a sense, like doing a way to model the way different players might not know what the other players are doing. So Bregman divergence descent step of mirror descent can be decentralized, and that would model a game in which players are decentralized. And then you can also stochastify, say, well, you don't even have a really good estimate because, say, you're using a really crappy app, so you don't really have a good estimate of how well you did. So the benefit of using that convex framework is that now you can generalize that to any kind of modeling you want. And the beauty of this is that so you can use several ingredients to finally show that now you'll have a stronger convergence to the set of Nash equilibria. So you still need this notion that the learning rates have to not go to 0 too fast, but they have to be square bounded. But if you do that, now the benefit is that, for example, for this particular learning rate, now not only you have proof of convergence to a set of Nash equilibria, you still don't know which one, but you also have a speed of convergence. The speed of convergence is both for the value and also for the state. So you can show also a speed of convergence of the state with respect to wherever it's converging to. And that speed of convergence is also written in terms of the Bregman divergence. So you can see every time we put more assumptions, then we have more guarantees of convergence. And so that's what we can get with this model. Now, of course, we don't know what Google's policy is. We don't know what Apple's policy is. So the next question is, okay, how could we show that this model is something that can model reality? And obviously, we don't have access to this data. And even the companies within themselves don't have access to each other's companies. So I'm going to just skip the numerical result, but I'm going to show you a little mechanical Turk implementation of this we did, and runs we did with humans to show that it's funny because you can actually show that this is the way people learn. So this is the online game we created. So this is a Mechanical Turk interface now, in which players log into their Mechanical Turk account, and then they play a game in which they're asked to route people from certain origins to certain destinations. So you could view this as the Google router guy, whoever is in charge of routing, in a sense, is going to play against the Apple router guy, and it's going to play against the Waze router guy, and so on. So everybody's competing for resources on that network, and everybody can adjust the way they allocate their flow, which again, is not what companies are doing for most of them today. Companies today are just giving you a shortest path. They're not solving a dynamic traffic assignment yet, all of them, without having all the information of the other companies. But let's assume they did, then this is what they would do. They would say, okay, well, I'm the guy running the Google app today, so if I want to go from here to here, I'm going to have, 10% go this path, and then another 10% go that path, and a third go that path, and so on. So you can play with the proportions. You don't know what the others are playing, obviously, but you know that they're playing the same game as you are. And then the question is, well, this is exactly the model we had before. So can we show at least that if we have real people playing that game, it does converge to a Nash equilibrium in practice, which you can assess because once you have converged to a Nash equilibrium, in a sense, you can see the travel time is equalized on all the path, and there's no incentive to deviate. And so that's what the game does. So people can look at every iteration of the game at the network. They can allocate the flows according to the slider rules, and then they can see how well they're doing on each of the paths. So for example, here you have a lot of flow on the blue path, and most of the flow the rest of the flow is equalized on the other path, and then you can see for every path which path is better and which path is worse. And so, so that's the way you build it. So people play together. They don't have access to each other's information. And what's interesting about this is that I don't know how people learn. Some people are maybe very fast learners, and some people are very slow learners. So you don't know the etas a priori if you were trying to fit a model to understand how people learn. But the process of understanding the learning rate of people is actually a convex program. So in the learning rate, so finding if I have access to all your data and all the choices you made, finding your learning rate according to that model is a convex program. And so that's one of the things we were very excited when we found out about this, because now we look at the data and we can try to understand people's learning rates. And when you look at people's learning behavior, I mean, it's interesting. Initially, people start to play and they do very poorly on one link and they do very well on another link. So there's a lot of exploration. And after a while, there is some convergence. And you can see how they learned. And one of the things, so when that thing stabilizes, and then one thing we're doing now is understand, well, if you can see how they learn, you can probably also forecast what they will do in the future. Yeah.
It's not clear to me why you would want to play Nash here, since you're playing this repeatedly.
Oh, well, you don't. It depends on who you are. If you're the government, you don't want to.
One of these companies, right?
Well, if you are one of these if you're the government, you don't want to play Nash. You want to play social equilibrium. You want to play social optimum, obviously. Yeah. If you're a company, why would you want to play Nash? Re-elected. Oh, if you want to be re-elected, yeah. Well, yeah. I don't know about the elections, but yeah. But okay, I don't know. It's a hard statement that companies would want or not want to play Nash. But today, if they don't give you something which is selfishly optimal for you, they will lose you as a customer because you'll find the other app that gives you something better for you. So in a sense, it's not that they're solving a Nash problem, but they are providing a solution which should be as close as possible from Nash if they want to keep you as a customer.
Yeah, I guess they don't want to deviate too much from. Yeah. If I give you a 10 minutes longer route to Palo Alto just for it to benefit the society because you're going to decongest 101, then you're not going to use my app anymore because I don't help you. I help society, but I don't help you personally. My problem is that if you only look at Nash and you're playing this repeatedly, there's a Nash that basically forces everybody else to do very poorly by threatening to do very bad things to them.
That sounds very much like North Korea.
Yeah, pretty much. You could try and, I mean, these companies could try and play these games. If
if you restrict your solution concept to Nash.
Well, but the thing is, okay, it's an interesting thing. We don't restrict our solution space to Nash. We make assumption on what the companies are doing, and we show that if the companies were doing this, then at best they're converging to Nash. Now, I think a logical step from what you're saying would be, okay, let's try to do other things they could be doing, and could we converge to something better than Nash? And that is a true question. Actually, there are a lot of interesting work, some of them done by Johansson in Sweden, where if you spoof people's cost function, that goes back to Balaji's talk, then you can converge to social optimum. So say you incur 10 minutes extra, but you get $2. Your cost function is now weight of time plus money. I can get you to converge to something different. And so that's probably one way to think about these things. If you want people to not behave selfishly, that's where you have to incorporate rewards, or like you're saying, maybe the North Korea way, penalties.
I wonder if maybe your question comes from the fact that you're thinking about the repeated game with a repeated Nash equilibrium concept.
And by the way, it's not a repeated
game, but with different with conditions that are evolving.
Right. And by the way.
What I wonder is whether Alex is thinking about it as just a one-shot game.
No, and it's not a one-shot game. That's the thing, is the system is never at equilibrium, because the results just show that in the first assumption, on average, it converges to Nash. The second one, it converges almost surely to Nash. And in the third one, it converges with a given rate to Nash. But the system is never at equilibrium. That's very important.
In your mind, do you think about the strategy as the route I choose today, or do you think about the strategy as the route I choose today, tomorrow, and every day?
Okay. In my mind, I think about. Okay, so.
You're not thinking about an extensive form game. I think you're thinking about the Nash equilibrium of the single shot game.
Exactly. But that's the equilibrium state. Exactly. So that's the point. It's a repeated. You could view that. Let's not use the word game for the iteration process. Like it's a sequential decision-making problem. Okay, no game, and. Okay, this is maybe the disconnect. I think you pointed it exactly, and it actually converges to a Nash equilibrium of the one-shot. Exactly. That's probably the disconnect. So because there's nothing in the sequential decision-making process about a game. It's just every day you're doing an optimization based on some criteria.
But if you're a user, you would stick to your app if it were good.
If the app is good to you.
You're not going to try all the apps every day and see which one gives you the best.
That's what Hotwire does for airlines. I mean, I don't know. I mean, it depends. It depends. No, seriously, this is a very interesting philosophical question, right? I mean, think about when you're buying an airline ticket. If there's an app that gives you the best price on average, would you still want to try? I mean, like, that's why Hotwire. So, I mean, it's a philosophical debate, but yeah.
Extremely different setting. Like in an airline app, you know that this is the price. On Waze, they tell me,
yeah, fair enough.
Because it's only 25
fair enough.
minutes. But by the time I get
okay.
there 45
yeah.
minutes
So,
later, it's
but yeah. Okay, so that's another very good point, and absolutely true. And people have infinite confidence in the app because at the end, Waze is giving you a travel time or whatever app is giving. Yeah, but.
And these are like no competition.
Absolutely. No, yeah. Fair enough. So the analogy in that sense is poor because one is like perfect information. Okay. Once you click, you paid that much. As opposed to you think you're going to take 35 minutes to go to work, but it turns out, oops, you took 45. Yeah.
It's the great question, what's the right solution concept? Whether it should be the one for the single shot game, the Nash equilibrium, or...
Yeah, so, okay, and so this is a very, and so that is another thing which is interesting. So most of the planning agencies today, when they compute the assignment problem, they solve the one-shot game, the Nash equilibrium, not even the dynamic traffic assignment, and in a sense that's what they use for their forecast. So there is a lot of work in the planning in terms of defining what is a solution of the assignment problem. And yeah, I don't think there's closure even in the practitioners community there for many reasons. I mean, one of them being that the origin destination data, the demand data is not very good. I see that we're nearing the end, so I don't want Dick to get mad at me if I go over time. I'm going to finish in 2 or 3 minutes, but I'd love to have more conversation. Is a good coffee conversation. So let me finish quickly. What's really amazing and really funny about this is that
when you look at the news, and I don't want to pinpoint any particular company, what you see in the news, I'm just not going to read them, I'm just going to show them, you can make your own opinion. And by the way, this is also true on the East Coast with other institutions. So basically, people assume, and this is perfect, we just had this conversation, people assume that because what you're doing is, best for you, shortest path, is good for society, which is basically confusing, like the front page of the newspapers confuses a Nash equilibrium and a social optimum solution, which we all know is absolutely not true. But what's funny about it is that, well, then people get upset. So if you live in Southern California, you know, and if you take an Uber to LAX or Burbank, you will see that you go through neighborhoods you've never gone before. Why? Because most of the Uber drivers use a specific app, and they will take you through that neighborhood. And so what is that? That is actually a displacement of something that might be worse than a Nash equilibrium into something that might be closer to a Nash equilibrium. So it's interesting because you have actually 3 levels. In an ideal paradisiac way, you have social optimum. Okay, probably never exist. In reality, you have something which is really bad, and actually steering it towards a Nash equilibrium might actually make it better. Why? Because people who didn't even know about these options will do something which is not even as good. So think about the early ages of the mobile internet. Would you really take the app that goes through the neighborhood that you didn't really know about and you think is dangerous? I mean, it took a lot of time for people to get to this, but we're getting there now. And so that's where you can see this steering from this really bad equilibrium to something which is closer to a Nash equilibrium, and that gets people really upset because, you know, they see more traffic in their neighborhoods. So it's interesting because then people start to want to sabotage this, and the way you do it is you pay grandma or grandpa to walk on the street with the app, pretending they're a car stuck in traffic. People have done that in the past. Okay, and if you're a city official, you built street signs and you basically built a stop sign to decrease the travel time in your neighborhood so people avoid it. So that's the way people defend themselves against it. I mean, the people get involved. And, you know, we've talked to many cities. The only way they can make people get out of their neighborhoods is make their traffic worse. And so you see if you see a lot of new stop signs and new street bumps, that's mostly because the locals have figured out that they don't want a Nash equilibrium. Okay, and they don't want people to steer traffic towards a Nash equilibrium because it's bad for their neighborhood. And so that's the type of work that we do now in the Connected Corridors program in Southern California, is trying to understand, you know, say if overnight 15% start to use Waze or any other app, what does it do to your local neighborhood? And so typically, you know, you get a start where you have a lot of people on the freeway to, well, cool, now you have less people on the freeway. And initially you had nobody in your city, and now, well, it looks like Bangalore. Well, maybe not as bad. And so what happened in the process of doing this is the more people use it, the more, you know, the travel times is better, it decreases on the freeway. And okay, first they go through that first route, first they go through this. Okay, they go to that first route. Okay, and then that first route gets really congested, so then the app figures it out, then they start to go through the second route. Okay, and congest the second street, so that's the second thing here, until they equalize, and that's a Nash equilibrium. So this is what's happening today. And of course, the speed at which this happens is slow. People are taking a long time to learn, to adopt, to start using the apps over and over, but this is what's happening. That's a real problem in urban planning today. And so that's the type of models that we're working on, and that goes back to, you know, what is the proper definition of equilibrium? And the truth is, it's neither social optimum nor Nash. It's right now is something different. And I'm going to stop now because I think we're over time, but basically maybe my last slide. So historically, I think what was amazing about the last decade is that the last decade with the mobile internet gave availability of information. Everybody now has access to routing information. Anybody can figure out within one app, click the shortest path. That's what happened over the last decade. And so now in the post-travel time optimal control era where, you know what's best for you and you potentially know what's best for society, how do we achieve it? In a way that is optimal. So that goes back to Balaji's talk. It's like, what are the right incentives that enable people to do the right thing? How can we make you want to waste 10 minutes of your time for a reward so that it's overall better for society, which is really what Balaji's work is. So I'm going to stop now, but thank you for the good questions, and I think we can talk more over coffee. Thank you.